Okay, aloha, talofa, half a day. Welcome to the 7th and last Pacific Desk webinar of the year. I'm Jennifer Strahl, the Honolulu-based Pacific Desk meteorology instructor, taking over for David today, our usual host for our webinar series. As you can see, our presentation today is on the Gálvez-Davison Index and its application to tropical convection. So before we begin, I want to mention that this webinar is being recorded and it's also being broadcast on Facebook Live. So we'll post the recording online for later access. For those of you participating on Zoom, please keep your camera off and your microphone muted. That just conserves bandwidth during the presentation. You can ask questions anytime during the chat box or using the chat box during the presentation. Or you can also leave a comment if you're watching us on Facebook. Just please introduce yourself by including your organization when you ask your question. We'll have some more time too at the end if you prefer to unmute yourself and ask your question through your microphone. So for those of us in Weather Service offices, we spend a considerable amount of time predicting daily weather. So of course, severe weather phenomena like tropical cyclones, those command our attention from time to time, but thankfully those events are infrequent. Synoptic scale features like troughs, convergent zones, those are often weather makers for us too. But because those are relatively large features are generally more predictable. They're resolved fairly well in models, even if the smaller scale or like the local effects aren't. Frequently, though, we are focused on trade wind convection, patterns where subtle differences in moisture and stability can make the difference between precipitation and not, or the difference between lighter and heavier showers. And those more subtle weather patterns give us opportunities to improve skill in our daily forecasting to be able to produce more detailed and therefore more useful predictions. So for example, we can make a forecast of brief showers over the next couple days. But if we have the tools that can help us distinguish that maybe tomorrow's risk of showers is greater than today's, or we might expect more precipitation from those showers tomorrow, that detail can be pretty helpful to the users of our forecast. And that's something that we encourage our training participants to do, to add value to their forecasts like that wherever they can. So in training, we often use precipitable water for assessing moisture in the atmosphere. And we know that if we have more precipitable water upstream in the trade winds, we might expect an increase in showers as that moisture approaches us. We also use things like CAPE or K-index to assess stability. But those have some limitations in the tropical and equatorial oceans, as our presenters today are going to show us. So today, our speakers are going to introduce another tool that you might not be aware of. It's already being used in other tropical ocean basins, and it's also available in the Pacific. So our speakers today are the Gálvez and Davison from the index that bears their names. They both join us from the NOAA National Weather Service Weather Prediction Center International Desks over in Maryland on the east coast of the continental United States. The WPC International Desks and the Pacific International Training Desk, we share a common mission of capacity building across international meteorology services. The WPC International Desks focus on South America and the Caribbean, also historically Africa and Saudi Arabia, and their training format is a little bit different from ours. So for those of you who have completed our Pacific Desk Level 1 training, our presenters are going to discuss some limitations of traditional stability indices that should sound familiar to you. If you've completed our Level 2 training, you'll see some resources possibly on MJO, equatorial waves that you might recognize. And if you have not attended our training before, we are thrilled that you have joined us today, and we hope that you come away with some useful information. So with that, I'm going to hand it over to Mike and Jose.
Right. Hi, Jennifer. Hello, everyone. You hear me well, right?
I do.
Okay, great. Well, thank you very much for the invitation. It's a pleasure and an honor to be presenting our work with you guys, and we hope you find it really useful. We know that some people in the basin have found it useful because, as you know, uh, forecasting convection in the tropics is very complicated, and there's not a lot of tools available. Therefore, Mike and I developed this index to try to help with that process. So I'm going to share my screen. And please let me know if you can see my screen. You see my screen?
Looks good from here.
Okay, perfect. Okay, let me get organized. Okay, so what we're going to talk about today is the Gálvez-Davison Index with an emphasis on forecasting convection in the tropics. And this was developed by Mike Davison and I we started in 2013, and we got a preliminary version in 2014. And we wrote a manuscript that is on our website on 2016. But this has been basically operational since 2014. And so what is the GDI? The GDI is a thermodynamic index, and this was developed by the WPC International Desks in 2014. And the goal was to improve the forecast of trade wind convection. It is a diagnostic tool. It is not a model. It basically uses model data or analysis data, and according to that, you can calculate the index, and it will diagnose whether your environment is favorable for different types of convection, right? So what it does, it relies on the vertical distribution of equivalent potential temperature mainly, and upon that and other variables, it tells you what type of convection you should expect. So the three main processes that the GDI looks into is, first, we have the column availability of heat and moisture. So we look at theta E to get that. Then we have the stabilizing effects of mid-tropospheric ridges and destabilizing effects of troughs. Could be a polar trough or a TUD or any upper trough that has a cold core. And then we will also look into the stabilizing and the drying effects of trade wind inversions. So, well, this is just quickly to show, this is last week, and you can see the GDI values. The higher values suggest that you have a higher potential for getting deep convection and higher rainfall amounts. And whenever you get into these yellows, oranges, and reds, usually there's a higher potential for thunderstorms. And this is a snapshot from last Friday, I think, showing this deep convection going off to the north of Hawaii associated with this upper trough. Then we have a TUD low located to the east of Hawaii, and you can see this deep convection going off in the yellows. And then along the ITCC, you can see some convection also going off to the south of this is, yeah, I think this is, yeah, to the south of this latitude. So basically, if you look at the GDI was able to capture the instability associated with the trough. It was able to capture this maxima in activity located to the south of Hawaii. And it was also able to capture this area with convection to the north of Hawaii. Of course, the specifics, if you get one or two cells that are producing a lot of a lot of high clouds, sometimes you won't be able to look at it with a lot of detail, but at least it will show you the area where you will get the convection. All right, this is another example of things that you can see with the GDI. I left this example. This was from the September webinar we did for American Samoa, and there were some interesting features going off during that period. So you can see cyclone Mindula at that time. The GDI is pretty good at finding these areas of high theta E in the column. So you can see tropical cyclones fairly well. And you can also get an idea whether the cyclone might be a rain producer or not. Of course, there's a lot of other aspects of the cyclone you cannot look with the GDI, but at least it will, you can look at the amount of heat and moisture available and whether it can be a heavy rain producer or not. So in this case, you can see that there's GDI is pretty high and it's a large cyclone, and it highlights feeder band convection, which is usually a challenge. So Mike and I also rely a lot on the GDI to find these feeder bands. You can see this upper troughs, fronts and convection highlighted by upper trough. You can see this belt of fronts here. There's definitely an extratropical system here. There's another front and less active convection along this front once you get to Hawaii's latitude and to the east into Canada. You can also see the ITCC. ITCC is pretty well defined in this particular case. And in the warm pool in the Western Pacific, there's a lot of deep convection, a lot of instability, which was resulting in deep convection at the moment. You can also see the South Pacific convergence zone and the systems in the South Hemisphere. And whenever you see these very dark areas in the GDI, this is usually highlighting the effects of the subtropical ridges. These ridges are usually associated with subsidence in a very large area. And this tends to dry out the mid-troposphere and allows for convection only to have a very shallow development. The convection is usually building up to 925, 850 hectopascals, and you have a lot of dry area aloft. So the GDI is also pretty good at capturing these areas where you shouldn't worry about having deep convection. Let me do something very quickly. I'm going to stop the presentation for a second, and I'm going to show the current conditions, just looking at to look what the GDI is suggesting. And then looking at the satellite image on the left, what I have is we'll have the geocolor, which is kind of a true color image. But on top, I have placed one of the RGB products. This is the Day Cloud Fakes Distinction product. And in this product, whenever you see these grays, kind of bluish clouds, they're low clouds. Whenever you start seeing these orange or yellows, basically, this is deep convection usually. And whenever you see these reds, it's usually cirrus, right? And I also overlaid the GLM. So this is the current satellite image. And what you can see is that the ITCC is very, very well defined just to the south of 10 North. And you can see these little lows on the ITCC. Over Hawaii at the moment, there's an upper trough. You can see it clearly by the this flow from the southwest with this cirrus shield. So there's definitely an upper trough, but just looking at the image, to me, the deep layer moisture is to the south of this trough. There is a plume of shallow moisture with some trade wind convection, very light convection moving into Hawaii at the moment. I mean, it's still to the east, but it's about to arrive. So just looking at these features on the GDI, you can see that the GDI is highlighting very well the ITCC at the moment. You can see values that are over 35, which are very often associated with deep convection. Then you can see the effects of this interaction between this moist plume to the south of Hawaii and the upper trough is also being captured. You can see a region of larger values of GDI just to the south of Hawaii, oriented from southwest to northeast, and this is what you're looking at. And then this area of shallow convection moving into Hawaii, it's hard to see. We need to zoom in, but gladly, we do have a domain that we implemented for Hawaii a couple of years ago. And you can see this signature very clearly on this domain. You can see this area of suggesting that you might have some trade wind convection, but the fact that the values of the GDI are really low suggests that you shouldn't worry much about it. You're going to get a couple of drops out of it, but it is capturing these features as well. So even in the dry season, the GDI is often good to capture this variability in trade wind convection. All right. Let me go back to the presentation. And why was the GDI developed? And the reason is that since in 2013, there was no method to quickly assess tropical stability. So basically, to assess tropical stability, Mike Davison's been working in the desks for a while, and what he had to do is basically go station by station and look at profiles, the soundings, and then vertical profiles of theta E and other variables. And there was no index to quickly have an idea of what was the distribution of these instability and potential for convection. So what he was also doing was trying to apply traditional stability indices. Here we have some, we have the lifted, the K, totals, Cape and scene quantities for convection, and then others, but they weren't working. And the main reason is that these indices were, for the most part, developed for the extratropics. And these indices, under certain circumstances, could be very skillful in the extratropics, as you can see, even in South and South America. But in the tropical region, none of these indices were producing very good results. So it was really a challenge to assess tropical stability quickly. This is just an example of what I'm talking about. And this is a cycle, a 12-hour cycle of convection over the Caribbean and North and South America and Central America. And basically what we're looking at is that IR4, one of the long wave IRs. So we're looking at brightness temperature. And you can see these cold tops are convective cells. So what we did was average that over the 12-hour period and got these results with the colder areas. Well, colder is in red in this case, which is counterintuitive, but these colder areas are basically suggesting locations where you had either colder temperatures and or you had more periods with convection. So in a way, it's a proxy to assess what type of convection you had. So whenever you get these really dark areas, or these are locations where nothing happened, it was mostly very shallow convection or clear skies. So the question is how the traditional indices resolve this. So we looked at these indices average over the same period, and we have the lifted index here, and you can tell that the lifted index really missed the areas where we had the convection. The lifted index was showing these areas to the east of this white contour, which is showing the high, the coldest brightness temperature. So it didn't do a very good job. We look at the Cape. The Cape was even worse for this particular case. Actually, it was showing the potential for deep convection in the area where we didn't get anything. And wherever we had the convection, it wasn't showing much. Then we look at the totals a little bit better, but still wasn't great. It still missed some areas. And then we decided to look at the K index, because the K index is, from all the indices available until 2013, it was the best one to forecast tropical convection, because it considers 700 hectopascal moisture, which the other indices do not. And this helps to build a more complete vertical profile, because what happens under 500 in terms of moisture and heat availability in the tropics is very important. So that's why the K is a little bit better than the others. And this is what the K produced on the top right. Oh, sorry, bottom right. And you can see that it was a little bit better than the other indices. It did capture this area of a lot of convection in South America and Colombia, also this area in Mexico. However, it missed some of the structures in for example, Western Cuba. Just Western Cuban areas just to the north had a bullseye convection. This didn't show it. And then the K also was showing values that were too large to the south of the deep convection. So the K tends to do that. It overestimates the coverage of convection. So we decided to generate the GDI specifically for the region, and look what we got with the GDI. With the GDI, it basically fits these areas of deep convection much better, and it does capture these areas with less convection better too. And it was also better at suggesting that these high areas of the K were not really going to produce any significant convection. So the GDI we're very happy with it. So the desired benefits with the GDI was to highlight all these processes that enhance wind convection that no one had really paid attention to whenever generating an index. And one of our goals, more concrete goal, was to improve over the K, which was the best tool we had available for the tropics. So basically, coming from something like this into something more like what you have on the right, be it more precise about the areas where we are expecting convective development. So how to generate a better index? So this is the process that we went through to generate a better index. So the first step is to identify what are the key processes that modulate convection in the region. And these are going to differ depending on where you are, right? So if you're in extratropical latitudes, you need to look probably a lot into fronts, into upper troughs, into upper jets, etc., right? But in the tropics, these processes are going to be a little bit different, and also matters where in the tropics you are. If you're in a region like the warm pool in the Western Pacific, where it's very, very, very warm in the entire layer, and you don't get these cold upper systems very often. Probably you need something more towards look into deeper in the troposphere, maybe not put too much weight into upper troughs, etc. So basically what we did was to try to find and make processes that control convection in the Caribbean and Northern South America and Central America and work with that. So the second process was to identify how these processes reflect in atmospheric variables. So once we recognized the processes, we thought, okay, what variables do we need to take into account to represent these processes? And the last one is the design of the algorithm, which consists on basically combining all these relevant variables into just one number that summarizes all these variable interactions. It can be a challenge, but it really helps the forecasters to just look at one number. So this is on step one, and as a background, one of the processes that we consider was what is called the moisture convection feedback mechanism. And this was described on the literature by Grabowski and Moncrief in 2004. So basically what it says is that convection convection that is foregoing helps to moisten the atmosphere and helps to favor the development of future convection. So if you look at the left here, we have two areas of convection trying to develop. Well, two areas of convection, right? One is deep convection that has made it all the way into the upper troposphere, and this is moistening the upper troposphere and is moving to the east in this particular case. And then we have an area of convection that is also trying to develop, but once it reaches this level, there's a lot of dry air entrainment. Therefore, the cloud doesn't develop very well. It starts struggling, and you end up with shallow convection or a cell that is very disorganized. But what happens after this period, this convection dissipates, and you get all these clouds basically disappearing. But what happens when a cloud dissipates? The water, the water is basically injected into the atmosphere as water vapor, right? This water vapor eventually moves to this region where you have some triggering mechanisms that were trying to develop this convection. And now the atmosphere is moist. Therefore, the convection develops very easily. So this is what is called the moisture convection feedback mechanism. So moisture really matters in the tropics, right? I think we all know that. So now the question, and it comes back to what Jennifer mentioned initially in when she was introducing the seminar, precipitable water, right? So Mike and I also thought, why not using precipitable water? And the answer to that is that there are other processes that also matter in trade wind convection. P1 is great, and yeah, don't stop using precipitable water. However, sometimes there are other features that precipitable water itself doesn't capture, particularly once you're talking stability associated with temperature gradients and moisture gradients that can be embedded between the precipitable water. So column, right? So what do we have in the tropics? In the tropics, we have the trade wind inversion, which is a very, very dominant feature that does play an important role in regulating convection. And also we do have, especially once you move into the into the edges of, not away from the equatorial region, right? Like where Hawaii is, the Hawaiian latitudes and latitudes of the Caribbean, you do get a lot of upper trough and warm ridge variability in the middle troposphere, and that will also play a role. So if you do have a warmer ridge, this will tend to stabilize the atmosphere, and this will tend to limit convective development. However, if you do have a trough around the periphery of an upper trough, this will highlight convection. So we look into these mechanisms, and we realized once we started testing the algorithm that we were producing better results than precipitable water and the other indices. So the second process is what variables to choose to produce an index, and theta E is one that we really give a lot of weight to, because theta E is a way to capture the content of heat and moisture in the column. It works great. It's very tied to moisture, but it does take into account the temperature effects. So what we did is, and also something else that theta captures, because of it captures moisture very well are these vertical gradients in moisture associated with the trade wind inversion. So this was really useful. Then we also looked at temperatures at 500. Most of the indices use them, and it's because they matter. They speak about the stability in the mid troposphere, and that's very important for trade wind convection, because convection is trying to grow, right? So it really matters what type of stability you have right above it. And so 500 temperatures work very well. And then the last thing we used was this different, well, we use these two levels, right? 700 and 950. Well, I don't have this right, but anyway, this is, we were looking at 700 and 950, and also the theta E gradient in this lower layer, because we wanted to resolve the trade wind inversion. So basically, these are the different variables that we considered. I'm going to go forward, and this will be kind of a conceptual model that we get once you look at this interaction with variables. So in green, you have theta E. If you have a deep column of theta E, of large theta E values, this is usually a region that is favorable for deep convection. If you do have an upper trough aloft versus a warm ridge, you will get more convection, and you can see in the results on the bottom, right? Both cells are going to produce convection and precipitation, but this one is very likely going to produce higher rates. And then we looked also at these subsidence inversion effects. So the whole trade wind inversion. So basically, it has two effects: a stabilizing effect and a drying effect. And this is taken into account into the GDI. These are just the data that you need to use for the GDI. It's 4 levels in the troposphere and temperatures and mixing ratios, and that's it. And we did produce a terrain correction, which shouldn't be an issue in most of the Pacific unless you go into really high resolutions. But in the Americas, as you know, there are regions that are very mountainous. So this does help forecaster to visualize fields. The values can be a little bit fictitious, but they help the forecaster to see things quickly. So this will be the algorithm design, which is the last part. And of course, I'm not going to go into the details, but the manuscript is available online. And these are the 3 components: the moisture column buoyancy index that takes into account the heat and moisture in the column. You have this mid-level warming index. So basically, the warmer the mid-levels, the lower the GDI. And then you have this inversion index, which says that the more stable, the lower layer, and the drier, so the more theta E jumps across that layer, you have a stronger inversion and lowers the GDI. So this is basically what it is. These are some GDI values and interpretation. This is on our website, this general table, and this is also on our website. But this is a general way to interpret the GDI. In reality, there are some seasonal variations and some regional variations as well. So it's always good to make a validation exercise for your region. But for the most part, this is a general way to interpret the GDI that usually works. And something that is very important to consider is that the GDI is not a standalone index. So it is very important to use the GDI, but you should also look at other variables, starting with precipitable water, which is also a thermodynamic quantity, moisture content. So that will help you to get a more detailed picture, but it is very, very important that you look into the dynamics, because you can have an environment that is really favorable for deep convection, but if you do not have a trigger that is going to trigger that convection or something that will enhance it, then it's hard to forecast. So you can say, oh, it may happen, but knowing whether you have this trigger or not would really, really give you an extra detail to the forecast that will be really useful to the user. So for example, in this graphic, we have the GDI and we have a couple of other fields. Some of the fields that we're plotting in this particular graphic are the low level flow in black, and then the upper flow in this is kind of a gold, if you can see it. And then in the bottom, we have this water vapor flux divergence. So whenever we have these brown contours, it's indicating that we have divergence in the lower levels. This limits precipitation. And whenever you have these green contours, it's suggesting that we have enhanced moisture convergence in the lower levels. And this acts in two ways. It is showing that you have a lot of moisture available, but it's also thus converging. And whenever moisture converges, it will feed your storm, so it will produce higher rainfall rates. And it can also trigger, if you're speaking about convergence in the lower levels, it could be a region where you're triggering convection. So that's why we're using these, because this will give us a further insight. Just looking at the upper flow, for example, here, I can tell that we have an upper trough, that this is a front. This is actually the current situation. I produced this graphic today to make sure we have like the most current. And we have a front in the Caribbean. Well, it's winter. We're getting closer to winter now, so we're starting to get these fronts in the Caribbean. This is a forecast, right? I think it's for tomorrow. And you can see that with the front, you have a higher GDI values. There's a second front here. There's a drier one, but this is the main one, that the rain producer. And you can see that we also have these green contours in this region, showing that parts of the front have this moisture convergence, right? So these areas I will need to pay more attention to. And another thing that we have is these gold yellow contours that show areas with enhanced upper divergence in a layer. So here it looks like I don't have a lot of upper divergence that will also help with rising moisture and precipitation. However, look at here to the northeast, we have an area that has moisture convergence and upper divergence. Also here in Panama, this is the ITCC, basically ITCC convection. So, and we also have a shear line that is organizing here. So these two regions I would worry about more, because we not only have high GDI, but we also have other features, dynamical features that are basically going to enhance our convection. However, if we look at, for example, this area in North and South America, the GDI is high enough. The values are high, but we do not have a lot of, we do not have an area of enhanced moisture convergence. Is very discrete, and we don't have an area of enhanced upper divergence. So I would expect something more like Irma's thunderstorms. I wouldn't worry too much about extreme precipitation for the region. And then if we look here at the Central Caribbean, the GDI is low, but we do have some moisture convergence there. And this will produce, this will actually enhance a little bit the values of the GDI. We don't have upper divergence, but this will, I would expect higher rainfall rates probably here with the shear line and also along the front. So in a nutshell, you need to look at the dynamics and other parameters to exploit the GDI to its maximum. Just looking at it alone will give you a general idea, but it will not give you the best forecast that you could produce. Okay. So now I'm going to speak about summary of validation findings. And these are for Central America and the Caribbean. So on the left, you have the R squared, which speaks about the percentage of variance that the GDI can be associated with. In this case, when you see values that are really high, over 50%, 0.5 or 50%, saying that for this particular period, just the GDI, without looking at anything else, was able to resolve over 50% of the variance of convection. This is pretty good. In Mexico and the Gulf of Honduras and most of the Northern Caribbean, as you can see, once you get away from here, in this time of the year, in the equator, this is very stable this time of the year. We have the cold tongue in the Eastern Pacific. So this was during the North Hemisphere summer. And you can see that the GDI doesn't work in these environments. And also once you get this continental convection, it can struggle as well under certain types of regimes, but for the most part, it works really well. But now the question was, how did we do over the K? But because our interest was to beat the K index, was to produce a better index. And whenever we have reds in this graph, this is just the difference of the R squared GDI, so GDI brightness temperature R squared in K index versus brightness temperature R squared. This is just the difference. And you can see that all the reds are areas where the GDI was better than the K. And we were amazed because almost over the entire Caribbean, the GDI was better. And in some places, for example, in the Cayman Islands and Jamaica, the GDI was able to resolve an additional 20% of the variance, same as the Bahamas, and the Greater Antilles, Puerto Rico, Cuba, over 50% and over 20% in Mexico. So we were very happy with these results. And then in South America, we can get a similar thing. Even though we developed the GDI for the Caribbean, as you can see, the Earth is North and South Hemisphere are a mirror in a way. They are a mirror. What changes is the topography, right? The topography can make it different. But in South America, the GDI results were great. And in Brazil, we were amazed because we got even better results than in the Caribbean. For Southeast Brazil, the GDI was able to resolve an additional 30% of the variance than decayed. So we were very happy with the results. Some of the operational applications of the GDI. It is great to track perturbations in the trains. Here on the right, we have an example of the GDI. The flow is 750, I think, averaged. And I don't know where I use this light blue, but this is showing areas of mid-level cyclonic vorticity, which represents the location of mid-level troughs. You can see here, there's a wave. This is an easterly wave that is, or a tropical wave that is moving into the basin. And there's another one here in Central America that you can track. And there's another one forming here to the east. So it's pretty good to follow the waves. And if you have a tide-induced trough, it's great as well for that. In this case, you can see here, there's a tide over the Bahamas, and you can see all this instability associated with the tide. So it's great for tracking troughs in the trades. And this could also be important to identify regions where you might get potential cyclogenesis, tropical cyclogenesis. Well, once you get into the cyclogenesis, it's a different story. The GDI will speak more about it, but at least it will show areas. What you want to see are areas with very, very high GDI and these circulations. So it's very useful for that. Something else that the GDI is useful for is looking into the ITCC or the net, the tropical convergence zone. This is just an example from Africa, but it's very good at capturing the location. And this is especially useful in periods when models resolve ITCC convection in different and flow in the very different locations. The GDI will be a little bit more faithful with the true position of the ITCC and associated convection. And it's also great for continental convection, especially once you look at the European model GDI. Then another benefit that is great is that the GDI is better over time. Over time, it is better than rainfall from the models. And this is because the GDI is less dependent on the convective parameterization. Like precipitable water, the GDI is more faithful to the larger scale transport of moisture and other fields. Therefore, the GDI, when time goes by, will be more reliable as a predictor of what is going to happen, say, next weekend, versus just looking at model rainfall. The model rainfall will eventually start diverging all over the place for different reasons. One of them is that you have this is what is called convective feedback. So what happens is that the model starts resolving its own thunderstorms and convection, and that will release latent heat and also change circulations. And then sometimes it will be right, but eventually over time that will generate differences that cause differences in model rainfall. So the GDI will help with that. And then something else is what I mentioned, continental convection, and also MCS formation, especially if you have nocturnal MCS. Whenever you see the GDI increasing suddenly overnight, especially during a period where you don't expect convection to increase, there's usually a signature that you may get some strong convection and potentially an MCS, depending on your synoptic situation. So you also want to keep that in mind, especially since most of you guys live in the Pacific, which has a lot of water, and you can have this nocturnal peak in convection. You should pay attention to this. And if you get a chance to get to look at the European GDI, that works pretty well as well for that. And these are my last slides. I don't want to take more time and taking a lot in my class's presentation coming. So some online resources. This is our main website from the WPC International Desk. So you have a link to the GDI here. This is the GDI website. This is this link. On this website, you can also see different things. You can see the GDI calculated for different parts of the world. We have, for example, a domain for Africa. We have a domain for Asia, the maritime continent. And of course, we have the Pacific domain and the domains for the Americas. But you can also see a manuscript. You can find a manuscript, but you can use to code the GDI if you want to code it, and also to read a little bit further about it. You have some presentations and some related studies. And this is the products that we do have now for the Pacific Basin. We gradually implemented some products for the Pacific, which is also available on the website. So this is an example of the domain for number. Oh, this is 5.0, sorry, or 5 for the entire Pacific Basin. And this is a domain that we have for Hawaii that we had it for almost 2 years, I think. And this is a domain that we just developed for Guam about a month ago. Thanks to their interest, they let us know that they were interested in looking into in having a domain for their region, and we were able to implement it. And also we have some domains implemented for Samoa. This is from our presentation 2 months ago, showing the domain for American Samoa. And in this case, we also have some extra loops. We have a European GDI loops that have the access is restricted, but if you're a NOAA member, you can look at it internally. And Mike is going to speak more about it, especially about how to apply the GDI considering other variables. And this is an example of some of the information that we have on the Samoa website. We also have precipitation that, of course, helps a lot to see where at least the model is suggesting you're going to get the rainfall. And then we also have precipitable water, which is always very important in the tropics. And now in this case, we have the GDI, but as you see, you have other fields that Mike is going to speak more about. And I think this is all I have for now. I don't know if there's any questions or comments before I pass it to Mike.
If you do have any questions, you can always type those in the chat box, or you can also unmute yourself, raise your hand. We have several different ways of getting our speakers' attention.
Okay, and Jose, something that I would like to add to your presentation, that one of the biggest challenges that we have in tropical weather forecasting is that the tropical atmosphere tends to be more unstable following convective development than prior to the convection. So, and that's what makes it even harder to forecast, where the traditional indices, they tend to help with to identify the environment leading to how the convection is going to be triggered, or how strong the convection is going to be once it starts developing. But in the tropics, is the opposite. The latent heat release causes the atmosphere to become more unstable the more we get along with the convective development. So, and that was one of the biggest challenges that we have to overcome when developing the forecast index.
Right. Yep.
Okay, I'm ready to share my screen.
Yep.
Okay, can you see my screen now?
We can. We can.
Let's see. Okay. Okay, let's keep on going then. So while Jose covered the development of the GDI, I'm going to go a little bit on how to apply it operationally for help you improve on your forecast process. Since I don't have a camera, that's me on the left, so you know what I look like, and you're ready, so Jose. So as Jose described during his presentation, so the GDI deals with the convective instability, and it focuses mainly on tropical and subtropical air masses. So when we deal with extratropical air masses, they are too dry, so it doesn't do as well when we're dealing with that. So especially when we're dealing with continental polar air masses, which you guys don't have that problem over the Pacific, since you deal mostly with the maritime air masses. And one of the advantages of the GDI that it takes into account the negative influence of mid-level ridges, and also the positive influence of upper level perturbations like core trough. And one advantage over the K index that it can clearly help you discern between shallow and deep convection. So as was indicated, the GDI is not a standalone index, so you cannot just go by the GDI and without looking at anything else and make a forecast. You need to take into account atmospheric dynamics when making your forecast. At the Weather Prediction Center International Desk, the methodology that we follow, we go with a forecast funnel approach for forecasting atmospheric dynamics. In that process, we tend to look at what are the sources of upper level divergence or convergence, because we want to identify what are the sources of ventilation. And as we've been talking about, we want to look at the column stability. So the GDI and the K index tends to be the best indices for the tropics, where the GDI tends to do a better area forecast. The SSI, the shortwater, and the lifted index, they have its uses, but it mostly depends when we have deep layer upper level trough. So when we have a deep top, that's when we would like to look at the SSI and the LI. Otherwise, the GDI would do a better job. And the CAPE, in the tropics, the tropopause is too high, so the CAPE always tends to be very high values, so it doesn't tell you much. In addition, Jose described that we look at triggers. What are typical triggers that can release the energy? That could be the mid upper level perturbations. Sea breeze convergence could be a trigger, diurnal heating, tropical or easterly waves, just to name a few. We can also have fronts of prefrontal shear lines, induced trough. Now we want to look at sources of low level divergence or convergence. Sea breeze front can be a source of low level convergence, also the easterly waves and the shear lines. Now, most important in the forecast process is going to be quantified moisture content. So when we look at mixing ratio, we also want to consider the dew point temperature and the precipitable water. Now, can we use relative humidity to quantify moisture content? And the answer to that question is no. Relative humidity does not quantify moisture content. It only quantifies how close you are to saturation. So you want to rely more when quantifying to parameters like the mixing ratio, dew point, and precipitable water. So comparing direct comparison of the GDI versus precipitable water, the GDI, the precipitable water will give you an idea that it is going to be a larger area of potential for precipitation than what it really is. And one of the reasons for that is because the precipitable water, when you're looking at precipitable water, the moisture content tends to be higher in the lower levels of the atmosphere. So you can have a very high precipitable water, close to 40, 50 millimeters of available water. But when you compare with the GDI, you will notice that it might be under an area of very strong ridge pattern that might be inhibiting the development. So just having the high moisture content does not translate necessarily to precipitation. When you look at vertical profiles of the equivalent potential temperature, you can have two possible outcomes. One of them would be that the air mass is convectively unstable, or that the air mass is convectively stable. The convectively unstable air mass would take place whenever the equivalent potential temperature decreases with height. When it decreases with height, you have cold air over warm, moist air, which induces convective overturning. When you have a convectively stable air mass, the equivalent potential temperature increases with height. That means that you have the lighter, warm, moist air over cooler, drier air. So there's no mixing in the layer. When you have that condition, you're basically defining the inversion layer. Now, looking at a vertical profile of equivalent potential temperature, so you have it on the left, that would be from the surface to 200. And this is a west to east cross section. And that's marked on the GDR forecast that we have in here. That's the line that you see here. This is the west to east cross section. Now, looking at a particular point, GDI shows very stable air mass nearby the Samoa Islands. And if you look at the profile, vertical profile of equivalent potential temperature, notice that the equivalent potential temperature, it decreases from 360 degrees down to about 349. So that's a sharp drop of temperature between the surface and 800. But once you go above 800, notice that the equivalent potential temperature is increasing with height. So in this area, you have very shallow convective instability. And in this area above it, you have a very strong subsidence inversion that is going to be capping development. And if you notice the entire area, you can see where the subsidence cap, how it is how it's presented in the atmosphere. It's going to be a lot lower to the left of the image and slowly going up as we go towards the right of the image. So that's my inversion layer. Looking at another point where the GDI shows a little bit of convective instability, if we notice on the profile, we can see that the temperature drops from 364 degrees at the surface down to about 338, maybe 320 degrees at 650. So this is an area of deeper convective instability than what we saw before. But again, we have an inversion just right above it, where the equivalent potential temperature increases with height. A third point that we are looking at, point C, same thing as we saw before. We're seeing very shallow convective instability with the temperature decreasing between the surface and 800, and then increasing above that. And you get to see where the other inversion is located. So before the GDI, this is how I did my assessment of the tropical air masses. I would go either cross-section or vertical time sessions, different plots all over the basin, across the Caribbean basin, trying to determine where the deeper instability was present and where the conditions were more favorable for thunderstorms to develop. So a very time-consuming process that was simplified a lot by the GDI, having the GDI available. So that's allowing us to concentrate on areas where the weather is going to be the most active, and then put less emphasis on areas where the weather is going to be more stable. Now, another example, this is farther to the south, and we're looking at areas where the GDI is showing higher values. So we're now looking around the mid-20s for the GDI. So that should be suggestive of deeper convective instability. So again, at point A, where the GDI is showing convectively stable, we see again very shallow instability with an inversion above it. At point B, we see again deeper change of temperature with height. So we have deeper convective instability. And notice something very interesting. We actually have a double inversion. We have one at this location where it's around 800, and then another inversion above it around 450. So sometimes when you're looking at the GDI, one of the things that you might want to verify that it might be showing a high value, but if you have the opportunity, take a look at the cross section or the time session to see the distribution of equivalent potential temperature. So once you determine that you're looking at either deep or shallow convection, then you want to look at the steering flow, because the movement of the sails as they develop, that's what you want to determine. Because if you're in one of the islands, you want to know, are they, once they form, are they coming towards my island, or are they going to go to the north, or which way are they going to be going? So by determining how deep the instability is and the potential for development, then you can determine if the steering flow is going to be controlled by the lower levels or by the mid levels of the atmosphere. So low GDI values is going to be controlled, the low level flow boundary layer is going to be controlling the movement of the cells that are developing. The higher the GDI, then you want to look at, you have deeper instability, so you want to pay more attention to the mid-level flow, 700. And if you have a conditions where you're going to be looking at MCS development, then the mean layer flow is going to have a bigger impact on how the MCS is going to be propagating. Looking at the illustration then, when we have shallow convective development, so it's going to be limited to the boundary layer of the atmosphere, most likely your 850 winds will provide a good profile on which direction the cells are going to be propagating. But once you start looking at the cumulus congestus, so this will be the towering cumulus, once you start dealing with towering cumulus, then you might want to be looking at the higher atmosphere, so at 700, for the steering flow that is going to be determined which way the cells are going to be propagating. And like I mentioned before, in the case of an MCS, then the mean layer flow 850 to 250 will give you a better idea on which way the area of organized convection is going to be propagating. Any questions? Is this clear? Or any doubts? If you need me to go over something again, please, at any time, please send a text and I'll be more than happy to explain it again. Okay, if not, let's proceed. Now, something that I would like you to keep in mind when you're looking at shallow convective development, that you can have situations where you can get having shallow convection doesn't mean that you're not going to be getting heavy rainfall amounts. And that's particularly the case whenever you have an echo training event. Shear line convergence tends to be a very good example of an echo training pattern that can produce heavy precipitation. Each one of the individual cells doesn't produce that much rainfall, but when they start training into a particular location, over time, the amount of precipitation can be fairly intense. So please keep that in mind when making your forecast. Don't just assume that because you're dealing with shallow convective development, that you're not going to be getting heavy rainfall amounts. Now, something that Jose and I have identified with doing forecasting in the Caribbean basin is the importance of the moist flux convergence. Now, this is not just low-level divergence or wind divergence or convergence. This has to do with the transport of moisture and the divergence of the transport of moisture. One of the reasons why this is important is because when you do the moist flux divergence, you're taking into account a mass component that has an impact on the static stability of the atmosphere. So whenever you have moist flux convergence, that's going to increase the instability of the layer. And whenever you have moist flux divergence, that's going to tend to enhance convective stability. So combining the moist flux divergence with the GDI can give you a better idea where you have the highest potential for development. Now, in this image, we have the wind vectors showing the flux, the transport of the moisture, and the contours is going to be showing the areas of negative divergence, which is your area of convergence. If you look at the flow, you will notice that the flow is confluing into what looks like a shear line pattern where you have a confluent asymptote. And when we look at the forecast of divergence, we see that that area is strongly convergent. So now you have a flow that is confluing, that is leading to mass convergence. So that's going to be enhancing all along that area, that is going to be enhancing the convective, the static stability, which could help enhance development in that particular area. So by overlaying the moist flux convergence over the GDI, then you can have a better feeling on where the convection is going to be more intense and where you're going to see deeper convective development. So in this particular point 1, we can see that we have an area of moist flux convergence. And in this case, we're using the inverse or the negative. So positive is actually convergence. So don't be confused by that. So looking at the moist flux convergence over where the GDI is stable, that's going to give you shallow warm tops cumulative development. Now, in this one, the GDI is increasing, so we have a better chance, deeper convective instability, and now we add the moist flux convergence, so we have a better chance for higher top and possible moderate cumulus. So while before we were looking at mostly 850 flow, now we're starting to look at an area where the 850 to 700 might be more applicable. At 3, we see that we have higher GDI values. The convergence is not as strong as what we have on the previous one, but we have deeper convective instability. So in this case, it might not take too much low-level convergence or flux convergence to start or initialize the convective process. So knowing now that the areas that we were looking at before, and we're looking at the 850 winds, so we know that at 0.1, the 850 would be fairly representative of where the cells are going to be going. And number 2, at least initially, the 850 winds can also have a good impact on where the cells are going to be propagating. But the deeper the convection gets, then we might want to start looking at the upper levels. And number 3, where we see that we have deeper instability and an increased low-level convergence, in that one, we might want to start looking at a higher level. Now, instead of looking at, now we're also considering the 700. So this is the streamlines in white, what we're seeing right now. This is the streamlines for the 700 height field. So number 1, where we have the shallow convection, it happens to be that the 850 and the 700 are pointing in the same direction. So it doesn't make that much of a difference. Likewise, as we go to number 2, it's not much of a difference between 700 and 850. They're both pointing from east to west. So any cells forming in this area, they're going to go straight to the west, especially as they continue building. Where we see a big change between the 850 and 700 is on number 3. Notice that the 700 flow is nearly perpendicular to where the 850 winds are. So in this case, most likely the cells, once they start building up, they're going to be progressing towards the south under the influence of this upper level or mid-level ridge pattern that is going to be steering it towards the South Pacific. Again, is this making sense so far, or some people are confused by this? No comments yet? Okay, so let's press on. Now, when we look at the mean layer flow, this would be from 850 to 250. In here, again, this is in the southern hemisphere. So what we're looking at, this is an upper level trough. Notice the influence or the impact the upper level trough is having on the GDI. So if you were wondering why the GDI was so high to the south, now you can see the why. The upper trough is having a big impact on the instability, and all along that trough axis, that's where we're seeing the best instability. Notice that with the ridges, we're not seeing that much instability. Some shallow areas to the north and farther to the south, it's mostly very stable. Now we can combine all of these parameters into one chart where we have the 850 winds. You can see it in black, the 700 steering flow in white, and then the mean layer flow in green, overlaying the GDI and the moist flux convergence. The first time you look at this is like, I have no idea what I'm looking at, but the more you get used to looking at something like a chart like this, it is basically becomes your one-stop shopping when making a forecast. You just see everything at a quick view, and then you have a quick idea on the impact that it might be having. And don't worry, we're going to be looking at some examples that could help make better understanding of this. So let's look at some practical application. So we're concentrating over the Samoas. And we can see that there's the trough that we saw before is basically advancing towards the north. So The first question, what is happening to the upper level trough? So we can see as the ridge builds to the south, we can see this ridge building is pushing the trough towards the north. How does the GDI changes in interaction with the upper level trough? And we can see that the GDI, especially in the area, the forecast area that we're looking at, you can see that the GDI is increasing, showing better potential for deeper convective instability. Remember that the core upper level trough is one of the things that is going to be enhancing the GDI the most. So let's take a look at some of the time periods that we were looking at before. So the first question is the air mass stable, unstable? So when doing your forecast, is it convectively stable or convectively unstable? So we have very low GDI values, less than 5. So the GDI telling us that the air mass is convectively stable. But we're starting to see in black some areas of moist flux convergence. So that areas of moist flux, low-level moist flux convergence in the GDI stable, they're going to be displaced by the A50 winds. Do you expect rain showers or thunderstorms? Rain showers, the GDI does not support a forecast of thunderstorms. It supports a forecast of shallow convection possible rain showers. Now looking at the next forecast period, this is going to be at 15 UTC, so 3 hours later. Notice what changed from the previous forecast. So if we go back to the previous one, notice where the trough was before, and look where the trough is now. Notice that the trough is approaching. So the closer the trough gets, the upper level trough, the more unstable the air mass is going to become. Now this is just visible image, and we can do a one-by-one comparison. Notice as the GDI and the winds, low-level winds suggest, the cells are moving from east to west. So they're just propagating from east to west with the low-level mean flow. And we can see possible deeper development to the east. So we're seeing a little bit of more development in this area than what we see closer to the islands at that particular time. So the closer to the GDI area, the deeper development we're starting to see. Now we go to 3 hours later. Again, still over the Samoas to the west, we're still seeing mostly stable, but over American Samoa, we're starting to see an increase in convective instability. The best moist flux convergence is mostly downstream from the islands at this particular time. The question is, do you expect rain showers or thunderstorms again? So still, GDI mostly suggestive, the low GDI values suggest mostly showers at this particular time. And what's different from the previous period? As I mentioned, that the GDI is starting to become more unstable, especially to the south and to the east. In response to the changing pattern, so we're still looking at the visible image that corresponds to that particular period. Notice shallow convection with the moist flux convergence, deeper instability mainly to the east, and the steering flow is still mostly representative of the A50. 3 hours later, so we're moving towards 21 UTC. So the GDI is increasing, continues to increase, and possible it might be responding to daytime heating in addition to the upper level trough. Still conditions mostly favorable for rain showers to develop, but something interesting, now that we're taking into account daytime heating and winds greater than 20 knots, we're going to start seeing streamers developing over the islands. And the main difference from the previous period is that the trough is getting even closer to the Samoas. Notice the deeper instability, and we're seeing more white tops to the east approaching the islands. And notice we're starting to see some streamers developing off American Samoa. Let's go now to 0 UTC on the 14th. Now we're still looking at slight increase in convective instability. Rain showers, but the winds remain strong at 20 knots. And the trough is getting even closer, and that's probably why we're seeing the increase on the GDI for that particular period. So the verification of that particular forecast. Notice the streamers are becoming better defined at this particular time as we go into the mid-afternoon hours. So closer to max heating. Deeper development to the north as suggested by the GDI. And as I mentioned, the streamers and all of the islands are showing an increase in streamers to the west. And as we go towards the next period, that's when we're seeing better instability just to the south. And still seeing some rain showers, mostly rain showers based on the GDI forecast, less than 10. So your 850 winds is still dominating the steering flow pattern. And notice increase in development at that particular time. So to the north and downstream from the islands, close to them. But something very interesting, notice this area, this wedge of convectively stable air that is approaching from the east. Notice that that wedge is really well defined and is being reflected in the satellite image. So it's showing an area of stability separating two air masses of more unstable air masses. So the current resolution of the GFS, I was really surprised by seeing how well defined that the dry slot was being reflected in the forecast. So the model did a pretty good job in identifying that. And notice that the dry slot, the impact that it's having before that, notice that we're not seeing that many streamers forming. And as the dry slot gets over to American Samoa, notice that the streamers disappear. So the air mass is becoming more stable. So I was really surprised by seeing how well the model identified that. Again, mostly shallow, so your 850 winds are providing the steering flow conditions. Okay, and this would be a 6 UTC. At this point, we're seeing that deeper convective instability and moisture convergence is moving over the islands. Now for American Samoa, we might still be seeing some rain showers still developing, but we have a better chance for thunderstorms over the islands to the west. The main difference from the previous period, notice that the trough is almost on top of them. So now you have max heating, moist flux convergence, everything indicating that you should be seeing an increase in convective instability. Now the forecast calls for thunderstorms. Looking at the images and the animation, we see some indications that we are looking at some thunderstorms development. So we're seeing showers to the north, and there's a good indication that we're looking at a CV downstream from the islands. Now, as we go from towering cumulo to cumulonimbus, we started to see some of the clouds spreading towards the southwest. So the 850s are from east to west, but the 700 winds they have a little bit of a east northeasterly component, and you can see the clouds propagating in that direction. You can see the turn right there. So the deeper convection is being forced to turn to the left of the 850 flow. Now looking at the using just the 10.3 images, you can see that the temperature of the cloud tops, they were close to minus 30 degrees centigrade. So definitely looking at the CVs popping in that area. And notice the shadow effect right before sunset. And you can see the shadow on the islands, Upolu. You can see the shadow from the deep convection just to the waist of them. So the GDI, as we've been describing, is a thermodynamic index. It's not a standalone index. You still need to consider dynamical processes as part of your forecast. And the GDI forecast is only as good as the model forecast. So don't come out saying that the GDI is not working. Maybe the forecast that you got from the model, the position of the upper level trough, or the moist plume that came with it wasn't well defined in the model output. But for the most part, it will do very good. And as Jose indicated, we have seen situations where when you look at the precipitation forecast of the model, you can see some differences between where the GDI favors the precipitation to develop and where the model is showing the precipitation to start. And we often see that the GDI provides a better resolution on where the activity is most likely to form, and it provides you a tool to improve on the model forecast. So remember that one of the reasons why the GDI works is because it is taking into account how moisture propagates across the atmosphere, which is controlled by the equations of motion. The precipitation scheme is basically a cookbook approach to forecasting precipitation. If you have certain parameters, therefore you should have precipitation. But remember, most of these models are calibrated for mid and upper latitudes. The GFS, they have played a lot of emphasis in calibrating it over the United States, over North America. And the European model is mostly calibrated for forecasting over Europe. So tropical forecasting is not necessarily one of the things that they're really concentrating on. So we need all the tools available to help us improve on the weather forecast. Where can we see the GDI? Jose pointed out in the WPC International Desk webpage. There's also another site that this is a commercial site, Meteorologist, and it used to be better. They made some changes to it, and there's a lot of ads that come out whenever you go to the webpage now. So it's not as user-friendly as it used to be. So I mean, you can give it a try if you want to look at the European model, and there's other models in there that you could also look at the GDI forecast. But if you want to go mostly with the GFS GDI, our page is available. That's it for me. Any questions? Anything that wasn't clear that you need me or Jose to answer? We're here to help you out.
So again, you're welcome to either unmute your microphone and ask a question, or you can type it into the chat box. We're also keeping an eye, for those of you over on Facebook, we're keeping an eye on the live chat. So you're welcome to type in your questions there too.
I have a question, or actually I have three questions. So maybe you just answer the first one. So you only have a product that comes out of GFS right now, or is there an ECMWF product as well?
Okay, we look at the GFS and the ECMWF, but we are not allowed to share the ECMWF output. We're only allowed to share the ECMWF output with NOAA agencies. So if it is a weather service forecast office, we can share with them, but we cannot share with anybody else. The European Center will not allow us to share it.
Okay. Okay, and so my second question is, have you ever tried running this, or do you run this operationally in any sort of mesoscale model?
We haven't, but we know that, for example, Mexico's Met Service, they've been doing that. So other agencies have been able to do it.
Yeah. And how would it compare, or it looks like with the large scale models, it verifies pretty well that it works well in general.
Yeah, especially at the resolution that we're dealing right now. With the GFS, you're looking at 17 kilometers resolution. But this is a big improvement. So you'd be hard pressed to find in more detail by going with a mesoscale model. I mean, these models are basically running mesoscale. This is what we used to call mesoscale in the 2000, early 2000. So yeah. So.
Okay, and then the last part of the question is about orographic effects. So a lot of the island convection, especially the lower level convection that's dependent on the trade wind flow, is often orographic.
That was one of the things that I was really amazed to see, that at the resolution of the GFS that we're seeing right now, and even the European model, the resolution that they're running, that they were able to pick up the downstream effects from the Samoas. So, and that's why I wanted to show that example, that even some of those islands, unless they're really tiny, then they will have no idea that there's an island there. But if the island is large enough, the footprint is being identified and the output of the models. But that would be a case that definitely you would benefit for running it at half a kilometer or no less than 1 kilometer. So definitely that will give you a better improvement. Yes, I agree.
Yeah, can I add something?
Sure.
Yeah, I was thinking on the lines of the orographic effects, and yeah, the GDI will pick as much as the model can pick, right? So that's depending on the resolution. So yeah, higher resolution models will definitely pick up better. However, you can still use the GDI, and some of the tools might show, for example, with the moisture convergence and knowing your wind speed. And if you see that the GDI is higher enough, but there's some other ingredients, and you know your topography under an environment where you have a decent amount of synoptic wind flow, you can always adjust by looking at what the GDI does and the other parameters, your precipitation and unlike orographic. And Mike and I have been working with Puerto Rico for a long time producing QPF, and it really works. If you just look at the GDI and know those variables and you know your orography, you can fine tune the forecast until you get the chance to have a high resolution model that is accurate.
Any other questions?
So I have one. I think that was a great introduction to the development of the index, and a really fantastic and detailed case study over Samoa and American Samoa that I'm looking forward to doing some as well. And we have a pretty diverse audience, you know, from like the equatorial region, like up in the warm pool, to more, you know, latitudes closer to Hawaii, Cook Islands, Guam. And so I know Jose had shown some images showing the relative performance of the GDI compared with like the K index. Have you done that for any other regions besides South America and the Caribbean? Have you published those yet?
No, not ourselves. I know some other people have done some validation locally for the region, but we haven't done it aside from that that one validation for those domains.
Yeah, so the U.S. Air Force has done validation over Africa to help them improve on the forecast over there. But the Pacific region itself, we haven't done, and that's perhaps something that you guys might want to do.
Absolutely,
I think that's a good research project for somebody getting their master's degree or doctorate degree. I think that would be time well spent.
Agreed. It would be an excellent, excellent project that would benefit really not just their own home country, but the region in general too. So anybody listening who's thinking about that kind of thing, we would help connect you to resources for that. Okay, any other questions?
Yeah, this is Rick Bulukanag from Joint Typhoon Warning Center. First, thank you all for the awesome presentation. So the gist I'm getting is that GDI has limited effectivity with cyclogenesis, tropical cyclone formation. What do you think are the main limitations for this, the main reason why it has a limited success?
Well, what I meant is when I mentioned tropical cyclones is that the GDI is not meant. It wasn't designed to depict tropical cyclogenesis. It was mostly designed to depict environments with heavy rainfall or different types of convection. So the fact that it's not like the tool you want to use for tropical cyclogenesis is just because it's not designed for that. But it will. I wanted to point out that it can also show some of the characteristics of tropical cyclones in terms of the rainfall environment.
Yeah, definitely would tell you that the environmental conditions are prime for development. And also one of the other things that we were struggling with before having the GDI, Jose made this important point, which is the feeder band convection. So showing the feeder bands, that's something that we were happily amazed to see it on how well it was depicted by the GDI. And we had a case a couple of years ago over the Caribbean, actually last year over the Caribbean, where the feeder band, they got more precipitation out of the feeder band than the storm itself. And some of the islands in Central America, they got almost like 3 to 4 days of continuous heavy precipitation just out of the feeder band. And the surprising thing is normally the farther north the storm is from the ITCC, that connection, they're supposed to be losing that ITCC connection. And at that moment, the feeder band should not be as effective. Somehow, this storm managed to maintain that ITCC feed and continue producing precipitation for a longer period than was normally anticipated to happen. So we are amazed at the results of what it can tell.
What about the southwest monsoon? It probably has similar dynamics, although probably on a larger scale. Have you guys done any testing on the southwest monsoon?
You're speaking about the monsoon in Asia?
Yes.
Or the monsoon in the US, in Asia. Yeah. Well, we look at it qualitatively. We had a request. I think it was from Thailand to implement the GDI for the region. So we have that maritime continent available, and I've looked at it qualitatively, and I cannot speak about a quantitative validation. But for the most part, from the qualitative feeling that I have, it does work well. Once you get into this deep tropical convection, when you have this warm pool and the processes are mostly driven by latent heat and not necessarily but a strong upper trough and trade wind inversions, the skill decreases a little bit just because the GDI is meant mostly for trade wind regimes where you have this trade wind inversion and oscillating upper troughs and ridges. But it still works. It still works because it places a lot of emphasis on moisture content in the column. So in a way, it's a little bit like precipitable water, but more adapted for the trade wind regime. So it does work.
That's great. We'll keep an eye on it. And you mentioned the last few slides that GDI is embedded in the GFS model. Is that correct?
Yeah. It's we have it on the GFS. This is what we can share, right?
All right, cool.
Yeah.
Thank you very much.
I'm going to share this link very quickly. I know the monsoon is ending, but I'm going to share it on the chat, the Southwest monsoon. And I wanted to add something to Mike's comment on the cyclones. I didn't want to cut you with the question, but so yeah, when Mike was talking about the feeder bands, and so basically the GDI is great to have a holistic understanding of the structure of the cyclone. Well, in general, I would say more than holistic, general understanding of the structure of the cyclone. So what Mike mentioned, the feeder band and interaction with remote areas is very useful. And something else is also when you kind of have if you know a little bit about tropical cyclones, so work with that, and you want to have an idea what the cyclone might do, and you know, a little extra to the official forecast, just your own perspective as a forecaster, the GDI can be useful because it can point, for example, dry air entrainment into the cyclone regions where you might get dry air entrainment. So say if you know some or work some with tropical cyclogenesis, you know that dry air entrainment in the southwest quadrant is not good for tropical cyclogenesis, so it will limit the development of a typhoon, for example. So those features, assuming that your model is believable, those features are captured by the GDI. So if there's going to be a dry entrainment event and your model is good enough, the GDI is going to show that dry air entrainment in the southwest quadrant. So if you're forecasting, if you're not like the main entity issue in the tropical cyclone forecast, but you're forecasting for an island that is in the track, and they're listening to you, you can always mention, you know, we're looking into this dry air entrainment potential, so we are not extremely worried. You know, you can add this extra to the forecast just by understanding these features associated with the cyclone. So you cannot use the GDI to forecast what the cyclone is going to do, but you can have an idea on the QPF effects and what it might do that could help with your local forecast. That's what I wanted to add.
Great, thanks for that. We're pretty much out of time, so we'll wrap it up. But if you have any further questions as you think of them, we can always connect you if you send us an email. We can connect you with our presenters today, or you can also find them online as well through their website. So I want to share a very warm mahalo to our presenters today, along with everybody in the audience. I think we span about 11 time zones for today's webinar, so we really appreciate you joining us either very early or very late. Before we go, I want to share a slide. Oops, but Mike, can you unshare your screen? Perfect, thank you. So we'll be taking a break in our programming for the holidays, and we're going to return after the new year for some more webinars, as well as some more additional training opportunities. So you can see there, we've got some in the works for 2022, disaster management, sea level rise, mudslides, fire weather, very interesting phenomena coming up for 2022, as well as some others that are not quite on the schedule yet. This Thursday is our Thanksgiving holiday here in the US, so we wish you all a very pleasant Thanksgiving. We are thankful for your continued attendance of our webinars, and we look forward to seeing you for the next one. So thank you, mahalo, aloha.
Okay,
Thank
thank you
you.
for having us over, and it was a pleasure. Okay, over and out.
Yeah, thank you very much. Happy holidays.
And to you as well. Thank you.